Welcome back, focused learners, to another explainer. Today, we're zooming way in, literally down to the subatomic level, to trace the invisible, honestly kind of wild, life cycle of a single neutron inside a nuclear reactor. It turns out this is a chaotic, high-speed hero's journey from a totally explosive birth all the way down to a sluggish, incredibly useful maturity. Let's get started. Release of more than 2 neutrons per fission on an average is a boon. If it were just 1 neutron per fission or less, fission chain reaction would not have been possible. Okay, let's dive into this, because this quirky little mathematical lucky break in physics, it's literally what makes continuous power, and really the modern world, possible. Think about it. If every split atom gave us exactly 1 neutron or less, the reaction would just fizzle right out. So, here's our roadmap for today. We're going to cover 1. The fission chain reaction, 2. The neutronic obstacle course, 3. Fast versus slow neutrons, 4. Achieving thermalization, and finally, 5. Anticipating reactor evolution. We've got a clear path from the chaotic birth of a neutron right down to its sluggish maturity. So, let's jump right in.
Starting off with part 1, the fission chain reaction.
And this brilliantly illustrates exactly what we're talking about. You can see how an incoming neutron strikes a fissile nucleus, and bam! The nucleus completely splits into these fission fragments, and crucially, shoots out new neutrons. For continuous power, the golden rule is that every single fission event must induce at least 1 more fission. It's basically a microscopic relay race where the baton multiplies every single time it's passed.
Moving on to part 2, the neutronic obstacle course.
So our newly born neutron faces a highly chaotic environment. It's basically navigating a frantic atomic pinball machine. And let me tell you, a continuous reaction is definitely not guaranteed. First off, a neutron might just whoosh right past and completely miss the fuel nuclides. Or it hits the fuel but just scatters. Worse, it could be captured without even causing fission, which is game over. Or, it could just leak completely out of the reactor system entirely. Neutrons are constantly being lost to these captures, leaks, and non-fission collisions. So how on earth do engineers keep the reaction alive through all that chaos? Well, they have to master 4 specific variables to control the reaction rates. Think of it like a rule of 3 plus 1. You need to control 1, the neutron density, which is just the population of neutrons per unit volume. 2, the atom density, so the nuclides per unit volume. 3, the reaction cross-sections, and then that absolutely vital plus 1, the neutron energies. If you don't perfectly control these 4 factors, the chain reaction simply dies. And navigating this crazy obstacle course requires some incredibly clever engineering, which brings us to neutronic design. This is the precise selection of reactor materials and their composition, based entirely on their neutronic properties, basically how they interact with our hero, the neutron. You are literally tailoring the physical environment to manage these tiny, chaotic particles so they actually survive their journey.
Which brings us to part 3, fast versus slow neutrons.
Now, what's really interesting about this slide is the dramatic difference in energy. On the left, we've got our hyperactive fast neutrons, fresh out of a fission event and just rocketing around with energies way above 100 kilo-electron-volts. But over on the right, look at the slow neutrons, tamed all the way down to energies below a single electron-volt. To make this reactor actually work, we desperately need to transform those chaotic fast ones into the sluggish slow ones.
So, how exactly do we tame them? Well, it happens in steps. First, boom, they are born incredibly fast, peaking near 1 mega-electron-volt and averaging around 2. They are screaming through the reactor. Then, they experience inelastic scattering. They slam into heavy fuel nuclides, and that massive impact drops their energy below 1 MeV, so they start to slow down. Finally, we get elastic scattering. Our neutron bumps into really light nuclides, like hydrogen. Bouncing off these light atoms saps their momentum dramatically, dropping their energies all the way down to the sub-eV range.
All right, part 4, achieving thermalization.
Okay, I know. When you first look at this Maxwellian kinetic energy distribution equation, it looks incredibly dense. But don't let the square roots and constants intimidate you. Translated simply, this is really just describing energy sharing. Our bouncing neutrons eventually stop losing these huge chunks of energy and instead just start sharing it, eventually matching the exact temperature of the fluid around them.
So, the crucial point here is this mechanism we call thermalization. This is the absolute climax of our hero neutron's journey, the moment it matures. Through constant energy-sharing collisions, the slow neutron attains perfect thermal equilibrium with its surroundings, officially becoming a thermal neutron. It has finally reached the optimal state to sustain the reactor's continuous power.
And look at this number, 0.0253 eV. What does that tiny, tiny number actually mean in the real world? Well, it corresponds to exactly 20 degrees Celsius. Our once explosive high-energy particle is now just comfortably chilling at a cozy room temperature. It's almost cute when you think about it, just matching the vibe of the room.
And finally, Part 5, Anticipating Reactor Evolution.
Now, I want to pose a question to you. We've talked a lot about what the reactor does to the neutron, but what happens to the reactor materials themselves over time, as millions upon millions of these thermal neutrons constantly react, collide, and split atoms, day after day, year after year?
Let's move to the next slide and see how this builds, because every single reaction actually changes the board. You aren't just splitting atoms, you're actively depleting the original fuel nuclides and constantly creating entirely new fission products and transformed actinides. The reactor's internal landscape is literally shape-shifting. So neutronic design is also about playing the long game, anticipating this chemical evolution over the entire lifespan of the plant.
Which leaves us with this final thought. Long after that very first atom splits, releasing its hyperactive, fast neutrons into the void, can we ever truly say reactor's intricate, ever-changing atomic dance is finished? The invisible life cycle of these materials is continuous, beautifully complex, and honestly, always evolving. It really is a brilliant feat of physics and engineering. Thanks so much for joining me on this explainer, Focus Learners, and as always, keep questioning the world around you.